Last tutorial we discussed the specific challenges we had with large models, and it's not on the complexity and on the conception of the things. It's more about computation time with combinatoric explosion, with memory, and so on. But even with a building of a size like this, on a laptop, it easily works if you're a little patient, even without any kind of optimization. So that's very important to know. And I forgot, it's very important to know that this building is 500 million Swiss francs. So which means the value of a code of this building, that you have all the things organized, is at least 5 million Swiss francs. And you easily can do it as a single person if you are trained with it in a few weeks, let's say a few weeks, and you have 5 millions. And I think you are with that in a similar position like these architects in Renaissance. They didn't have to make the whole thing for a building. They just ran around. They had been state of the art in technology. They made these perspective drawings of new buildings, and then they ran around, made the archaeology. They got a huge capacity in intellect, and they sold it. And they sold it 2 or 3 times in their lifetime, and that's what it. So there were no big body jobs, not hard working all the time. It was more on talking, knowing how the work works, and selling it 2 times in a lifetime, and that's it. It's completely enough. Very interesting to see. Whether you can do it on market, it's another problem. There's a problem with the company here. It took very, very long to find a niche how to go into the process, in the regular process of architectural design, because it's not this kind of architectural design is not compatible with these phases of design and how it should work. And nobody is giving you the millions. They prefer to to work a lot to keep the money in tracks established. And if you want to change it, it's a big deal. So that's a key problem. It's not the technology, interestingly. But now let's go to another kind of problems. What is if the geometry is not this regular? So there's another colleague of mine, Christian Keretz, and I started with his impressive building. It's a house with 1 wall by Christian Keretz. You can look it up here. This is how it looks. Okay. And again, we make a simplified version of that, and I show you how this works. So this is quite interesting, again, to see how to go with any kind of architecture in the same principle of coding. So I developed some helper functions to get the principal floor plan. You can go in and look there because it's a little of geometry involved. So let's go here and then initialize these helper functions. Yes. So now I get a floor plan, a specific floor plan. So this is a nice one, and the moment you redo it, you get another one. So it's a generator of buildings like this, which is interesting. So now for geometry. So we get the coordinates. So you can do it by hand, for example. Draw it by hand. This is a specific setup. Draw it by hand, takes the coordinates, and then you are done. Make a sketch and scan the sketch. So these are the points. D1 of the wall. can check it. So these are the coordinates in 2D because this generator is only 2D. So what we do is we have these points. Now we go for the vertical, as we did it with our examples before. We say the wall is this is the wall. It's O, and it's only from the floor to the bottom. For example, if you have a kind of ornament, and then you can put, for example, in the facade, I made it say O1, O01, O8, 10. So I have 4 points in the vertical. So this is the vertical. Now we get for the 3D points of the wall and the facade, we simply apply these things to all these 2D points. By that we have these coordinates. So we will see how it looks like, and I think you can read the code. These are the vertices. So this is the objectivity, this is subjectivity. So lengths, so we have 66 in this case, and then we look at it as a graph. As we did it before, this is how it works. On the cloud, it's always a little tricky. So you see on the facade we have 4 points in vertical. With the walls we have 1 point in vertical, 2 points in vertical. Now we need the edges. Go for the edges of the facade in the topology. So, as we've seen here, facade is different from the wall. Now we have just coordinates, and now we need a certain key to distinguish between the facade and the wall. And I take this Z direction as a key. So therefore, the keys is so the coordinates at the point 0.1. So this means these are the coordinates at the facade with the 0.1. So now we take that and say we want to have towards these points around the facade, we want to have all the points which are an X and Y on the same position. So to get the 0.0, 0.8 and 1.0 at these points. And by that we exclude the wall. So we can do it by hand, but this is not a proper way. You always have to take keys and drag. So this asks all X, Y, and Z whether it's member of these coordinates here, X and Y. So, and now we not only have, you see, 0.1 at 0.1, here these X and Y at 0.1, but all the same X, Y at 0 and at 0.8 at 1, and so on. So this is done by these functions. I think you can try to read and understand how this is done. So now we look that where these points are in the list of coordinates. In this case, it's quite trivial because it's a one-to-one. But if this is not in a regular order, then this is important. So this maps the coordinate F and their list, because this is a sublist of the coordinate list, and this says element number 5 of facade coordinates is element number 5 of coordinates. So a double index needed. Now again we do the distance matrix, so this should be very fast because very few points. So, and then this says there's a distance 0.1 from 1 to 2, 0.8 for 1 to 3, 1.0 to 1.4, 1.0 to 1.5, and so on. So this is how the distances are, the distance matrix is. So now we look which kind of distances are available. We had it before. And then we see, because we are in computational number, different from the large building. Now we have computational numbers and we have problems with the computational errors, but we are with these very specific ones, so we can ask for equality. So, but we will see how it works. So now we ask which are of between 0.00 and 1.001, which are on the facade. Most of them are on the facade. So let's look at this. And these are the lines on the facade with which the length of 1. We can show that. These are this is the around, because the algorithm here makes always around 1. Segments, same glass, around 1. So these should be the horizontal lines. We are here. So we can do the same thing now with the verticals. With the verticals we know it's either 0.1, 0.7 or 0.2. So because we said 0.1, 0.8, 1.0, so these are the differences. So we sort this, and now we get around 100 something vertices, edges of facades. So we had the problem that with the facade, on the horizontals are around 1 with a little tolerance. The verticals are exactly 1. So we don't want the verticals because they are subdivided in 3. Therefore we have to delete the verticals. This is done with this function. So now we are around 90. Good. If you want to see that as a graph, very slow on the cloud. Then we see these are the connections around, properly done. These are the edges of the facade, and we call that edges facade. Edges of the floor, similar procedure. We look at the coordinates of the facade at 0. So we use the facade and take them at 0. These are the coordinates of the floor. So this excludes the 0 points of the wall. That's good. It's important that this is because of the scene and the harmonics of things. So it's important that you don't do this by hand. So you always have to go for this neighboring, and you have to readjust the topology by geometric means. By that you get the things communicating and give that a sound. So it's not clear to understand, but if you make that explicit, you have manual work. and the charming thing of that is gone. So you always need these keys, and these keys towards the topology needs to be geometric, and towards the geometry needs to be topologic, and by that the whole system runs and gives surprise and stays vivid. So that's very important. So with that here, we go for the, what is this? Let's have a look. These again these are the links. So we have now, and now this makes sense. It didn't with the facade. Now the first or the second point here of the floor is a fifth point of the global coordinate system. 9 is 33, and so on. So these are our links. So we use these now here to find the floor, and for that we need to find the shortest tour. So, and here we go for a round trip around these things. So we can have shortest tour is FL, all these coordinates here, can check it. It's interesting graph. So if you have points, they always find the shortest tour to meet all points. And because our points are here to go on a map, and because our points are more or less a circle, it's very clear that we get the floor and get these points, which are irregular, in a proper sequence, which is a topological question, and this is a topological algorithm doing that. If you want to have a graph for that, display that, then this connection should be proper. Here we are. Good. Then we have the floor. Same with the roof. Another algorithm we are using. So the coordinates of the roof is the coordinates of 1. So we want to have with the construction of the roof, we need the wall, therefore we can't exclude it like with the floor. And therefore we have all the points which are on z equals 1. That's our key. So we again map it, the two lists, to get the source, keep that. And now we make a Delaunay mesh on these and put that. So this is interesting to see. Delaunay mesh works like this. So we have these coordinates here, and they make this kind of stuff. So they triangulate these points. And because we have a nice surrounding here, we have the wall, we get a nice triangulation. Put that towards our indexes using VR links. Put it these sort of original indexes, gives us indexes to the lines. Put that to the graphs. Then we are in 3D with the roof and have a certain construction there, which is interesting. So it is a problem here with the Delaunay algorithm. So we have an edge which is very long and which is here, and you can cut it in a improvised version and say I don't want to have the lines which are longer than 2.5, for example. Hopefully this works. And if we now make the graph, then this edge should be deleted. Looks not too bad. Make it 2. I'm not sure. Again, I have to check it precisely. Ah, nonsense. E-roof cell. Ah, we have it here. Okay. Now this should work. Put it, and there we are. Edges of the wall, always the same. Now we take, we have the facade links, we have the links of the facade. So what is a facade? And the vertices which are not with the facade are with the wall. So we use this set operation complement. Therefore, these are the elements of the wall. We inspect these points here. So on the structural implication, again, this is a fast and a little ugly version, because we imply now that our algorithm is doing it in a proper sequence. So we should find the sequence. It's not so trivial, so I didn't have implemented this algorithms. I take it. And what you now see is, with our points, if we put that to a line, then we get this zigzag, up, down, up, down, up, down, but it's on a proper line, because the algorithm delivers it as this line in this structure. So now if we always take each of, we partition that into 2, and then we make lines of that. Then we get the verticals. If we make a transpose of that and make lines of that, then we get the horizontals. So can check it and why this is working. Interestingly, simple combinatorics to do all this. So with the combinatorics with topology is they are siblings. Or it's always the same thinking, and it's interesting. And I think you need a kind of mastership in working with it, with this transpose, and how to make the lines, how to make the connections, and how to organize and partition space. So this is in topology. This is interesting to realize. So walls is just these two combined, and then we have all these numbers, and this is the graph of the wall. Here we are. All edges combined. Wall, facade, roof, floor. And they all somehow organized the same way. I think you got this idea. And you simply have to play it. And then here now a graph with all the edges. So what you see is that with the facade, with the roof or with the floor, we have double edges, and because it's not about geometry, it's just about the connection, connectivity. Or we can, for example, this might be interesting, if we don't say there are coordinates. If we skip the coordinates here, then you see what's actually there. So it's a graph like this. So you can have different functions to spread these, spread the vertices and edges on a flat paper, and this is how it works. So, and we are just walking within the graph, and then now the faces needs these four cycles. So, and just put it back into shape. Then it's our building. Good. To get rid of the doubles, I think again it's not a building, yeah, it's a graph, and we don't want to have the doubles. So therefore, a double is, for example, if you go from edge 15 to 18 and from 18 to 15 or 15 to 18. So all this it's unidirectional, but in our code, as you've seen here, it's like this. 5 is undirected edge. You can have directed edges and undirected edges. So then 95, 60, and so on. And then they are doubles. So they are doubles because undirected, whatever direction they have. And therefore, I sort all the edges, which means I always get the smaller index prior to the higher index. And then I delete the duplicates. So if I do that and assign that to edges, then it's different, so it's a little less. And if I render it now, everything is singular. So here we are with a proper graph of our building. Good. Now the facing. We have the graphs, the edges. This is what is our status. This is just parameters. So this is how I can show you again. So this is the default layout of graphs. So this is ugly. So therefore I made the options for graph and set them like this. Okay. Then you don't have to bother. Now it looks better. This is what we did in these drawings here explicitly. Now we don't need it anymore. So now we have a nice graph for our purpose. So now, for example, we can ask for the roof, the edges of the roof. We sort them, undirected edges, say highlight graph, and now we can do these kind of things in this data structure of subjectivity. So, and like in graph, again, we can find cycles. We want to have up to 3, or we can make explicit 3 with these here in the roof. So we get the 3 of the roof. These are the faces of the roof. Now we say we want to have the edges, sort, faces here, F facade. Now we go for the facade with the roof, and here we want to have explicit 4. here we are, and we see that. Okay. Ah, yeah, we didn't do it here. This was separated here, therefore. There's the roof, we'd seen that. The cycles, here it's one command, the facade, the cycles, all around here. Now we go to the wall, and we want to have 4 as well. And because this building is randomized, you will have different numbers here if you play around with it. This is facade, and this is the floor. We just take it as it is. To make it a single polygon. So now we use and put that to a mesh region. Polygon of the walls. Take the coordinates because we are in the objectivity. So we take the coordinates. We put the polygons of the wall, the facade, roof, and the floor. We have certain style parameters, options, and we synchronize it with something, I don't know. Let's have to look it up. So now we get a combined mesh region of the building. Yeah, you see it's 2 is index. Now we have here the numbers. Now we can have an index of and 54 as a reference. No, not this. 54 as a reference. And now we got profile normals. Everything is in sync with the faces. Go for, yeah, let's see here. What do we have here? Mesh highlight. All the faces here. Again, we have now a geometrical thing. So we have the area. We know these are around 0.7 in size. These are these glasses of the facade, and we can select them by area. So these are all these building information models. So this is for measuring and counting the subjectivity of the objectivity of things, and with mesh regions. So we can go for others. 0.1 in size. So yeah, we go for measure of the areas, and the area should be 0.1. We also can go for the lines and the length of the edges. 0.7, take the 0.1 from above and have a combined highlight just to play around. Here we are. So these are two functions, helper functions. to get a list of all the elements. So we have, for example, we can get, yeah, okay, don't do it. Take the first one, and then you see it's a polygon of the roof. So we take the first of it. So to get the coordinates and the code, not this iconographic representation. So it's a polygon of this in space. So and this puts it normalized to 2D because this needs a production in factory on a table. Yeah. So we have to put that on a table and then transport it to the site at a certain position. So by that we need this transformation function. Put that to a point 00 on the machine, and therefore these are the panels. And if you want to put, it's a function to do this transformation for all these elements. And now we get all the elements to be produced in factory, and then bought and put it on site. So that's what I wanted to show you. I think you get an idea how to manage that. There will be 2 more chapters. One is on form finding via civil engineering, so giving hanging, change, minimal surfaces, and so on, and have then these kind of partitioning and definition of the one-of-a-kind elements for the construction. And we will go to robotics, how to produce these things in factory and then on site. So I think that's it. Thanks for watching, and see you in the next tutorial.